Hello, we are doing homework number 12, number 2. Show that h of t equals to the f of the conjugate of t0 minus t is the best receiver that maximizes the output signal to noise ratio, where input f of t is a deterministic signal and n of t is a wide-sense stationary process white noise with unit spectral density. Here, t0 represents the output decision instant. Plot the filter response h of t when the input f of t is a rectangular pulse of duration t, and the output decisions are made at t0 equaling to t, t0 equaling to t over 2, and t0 equaling to 2t. Okay, so we start off by examining the signal to noise ratio, the original ratio first, and we do a series of conversions in order to illustrate what we are looking for. So our signal to noise ratio over here, the Greek letter rho, is equal to s of t naught squared over divided by the expected value of w of t squared. Both of these can be converted to 1 over 2 pi times the integral from negative infinity to infinity s of omega e to the j omega t naught d omega squared, that quantity squared, over rww at 0, because we know that n of t is wide-sense stationary white noise, so the expected value of n of t is equal to 0. It's also good to note that the unit spectral density s of omega also equals to 1. Actually, there's one thing I forgot, but let's just keep going on with this. The one thing I forgot was that, so you know that x of t equals to the f of t plus n of t. That's our input, right? And we have our process h of t, and we want to find our output. Well, our output is y of t, and that equals to y of ft plus y of nt, and we can do that because the convolutions are linear. And so because of that, back to examining the signal to noise ratio. So we have this. After converting this to this, we convert this further to 1 over 2 pi times the integral from negative infinity to infinity f of omega h of omega e to the j omega t naught d omega, and that quantity squared over rww0 equaling to 1 over 2 pi times the quantity of the integral of from negative infinity to infinity h of omega squared times SNN omega, which also equals to the variance d omega. And so we can do a bit of cancellations here. We can cancel the top 1 over 2 pi with the bottom 1 over 2 pi. So here we have 1 over 2 pi left. We can pull out the variance, that is a constant, and we get left with, on the top, the absolute value of the integral from negative infinity to infinity f of omega h of omega e to j omega t naught d omega squared over the integral from negative infinity to infinity h of omega squared d omega. And so at this point we use this little something called the Schwarz inequality in order to figure out h of t. And so we want to maximize the signal to noise ratio, so we set the inequality equal to less than or equal to 1 over 2 pi. So here's the Schwarz inequality illustrated. 1 over 2 pi times the integral from negative infinity to infinity f of omega squared d omega over the variance. So after all that, h of omega ultimately equals to the f conjugate of omega times e to the negative j omega t naught, and conversely h of negative omega equals to the f of omega times e to the j omega t naught, further showing that h of t equals to the f conjugate h of t equals to the f of conjugate of t0 minus t. So if we set t0 equal to, so our original t0 graph that shows that it is a rectangular pulse of duration is over here. So we see f of t and f of negative t. And so following this equation over here, so over here we have f of t over 2 minus t. So basically you flip that over and you move it. So, right, your original one is here. Let me see how I can do this. Okay. So this is your original one. So we flip that over and move it half a step forward, and that's what we did here. Over here, it's just t minus big T minus little t. So that's B. And then over here we have 2t minus t. So we basically just move this. Actually, we flip. Sorry. Okay, so minus t, we have t. So for B, we have, we flip this over because of the negative t, but we move this plus 1t, so here, and that's how we get B, right? We have the negative t, we flip this originally, but move it t, so we get back the same thing. And over here, we flip the original from 0 to t over, but move it 2 spaces over, so to t to 2t, and that's what we get here. And that is homework number 12, problem number 2.